Hi everyone. So in this video, we're going to learn another way of evaluating limits. And this is actually going to be kind of the main way of evaluating limits that we'll be using moving forward. So we'll see that in certain situations, you can use algebraic simplification in order to evaluate a limit. And it will basically make our life a lot easier than having to test out numbers or look at the graph or things like that. So before we get into that kind of like main approach that we're going to be using, there are some rules that I just need to kind of get out of the way and tell you. These are not really rules that we're going to be using directly so much in this class. We might here and there, but they're just kind of things that are sort of underlying a lot of the other stuff we're going to do. And I feel like I have to kind of tell them to you. So if the limit as x approaches a of f of x, and the limit as x approaches a of g of x, if those limits both exist and are finite, so meaning that they're both finite numbers, they're not infinity or negative infinity. So you have two different functions, you're taking the limit of them. If those limits both exist and neither is infinity, then basically, if you combine the functions f of x and g of x in different ways, you can combine their limits in the corresponding way. So first thing that's true is that if you're taking the limit as x approaches a of f of x plus g of x, that's going to be the same thing as taking the limit as x approaches a of f of x, and then adding that to the limit as x approaches a of g of x. And then same thing actually if you're subtracting, so I'll just add like a little plus or minus here. And then another one is that if you're taking the limit as x approaches a of a product of two functions, so f of x times g of x, that's going to be the same thing as taking the limit as x approaches a of f of x, and then multiplying that with the limit as x approaches a of g of x. So next one you might guess is division. So if you're taking the limit as x approaches a of f of x over g of x, that's going to be the same thing as taking the limit of each individually and dividing them. And there's one kind of extra provision we need in this case, which is that this is not going to be true if the limit of g of x is 0. So, because then you would be dividing by 0, right? So that just wouldn't really make sense. And then one more. So if you're taking the limit as x approaches a of a number times f of x, that's going to be the same thing as pulling that number out and then just multiplying that with the limit. So again, and I'm just going to write this down so that it's in your notes. You know, we're really not going to be using these rules directly so much, but there just might be some times in the quarter where they kind of come up, and so that's why I just want to make sure that we have them stated. So we won't be using these rules directly very often, but they might come up. Okay. So now that we have that out of the way, we're going to talk about the actual methods that you're going to be using to evaluate limits for the most part. So the first method we need to talk about is something that's called direct substitution. So direct substitution is kind of what it sounds like. So basically, direct substitution tells you that for certain types of functions, to evaluate a limit, you actually can just plug the number into the function. And as we mentioned in yesterday's video, those usually aren't the types of situations where you're going to be taking a limit, but you might. And in those cases, you can just plug the number in. So what types of situations can you just plug the number in? Basically, if f of x is a nice function, and so I'm going to list out a whole bunch of different types of functions. It's basically all the different types of functions that you would have been exposed to at this point from pre-calculus. So if f of x is a constant function, so a constant function is just a number, right? Like f of x is equal to 5 or something like that. A polynomial. So remember, a polynomial is where you're adding up different powers of x. If it is a radical function, so a radical function is a function involving a square root. A rational function, so a rational function is when you're dividing like a polynomial by another polynomial. A trigonometric function, so those are the ones you learned about in 142, pre-calc 2. An inverse trig function, and also could be a logarithmic or exponential function. Did I spell it right? Exponential, yes, function. Logarithmic function. Or any combination of those. So you could have like a, e to the x plus sine of x, or square root of x divided by ln of x, things where you're combining these different types of functions. So if you have any of these types of functions, and then this is the really important part, and additionally, the function that you're dealing with is defined at x is equal to a. So if that's the situation, then to take the limit, then the limit as x approaches a of f of x is just the same thing as plugging a into your function. So this is the rule that's called direct substitution. So we'll do a couple of examples like that in a second, but I just want to make it clear, what are the situations where you cannot use direct substitution? So when can you not use direct substitution? Because really, like if you look at that list of functions we came up with, that's like every type of function that you've really encountered, right? Like there's not really other types of functions out there for as far as what we'll even see in this class. So what are the situations where you cannot use direct substitution? So one situation would be if f of x is a piecewise function. So piecewise functions, as we saw in yesterday's video, they're just kind of funny, right? So with piecewise functions, that's where it's always really important to test the left and right limits, because they're not necessarily gonna agree with each other. So piecewise functions can have all sorts of weird mismatches and jumps in the graph, things like that. And so in those cases, you cannot use direct substitution. And then the other case where you cannot use direct substitution is if your function is not defined at the value where you're trying to take the limit. And so those are the types that we were doing in maybe 2 videos ago. So, trying to evaluate a limit and you're like, okay, I can't plug this number in, let me test out numbers instead. So yeah. Okay, so let's see some examples where you actually can use this rule. So let's say that you were trying to evaluate the limit as x approaches 1 of 3x squared plus 5. So remember that limits don't care what's happening at a particular x value. So it basically doesn't matter that this function is defined at 1. The function is still kind of heading towards that value. And so we can just plug in 1. So if we plug in 1, we get 3 times 1 plus 5. And so that is equal to 8. So basically, if nothing goes wrong by plugging in the number, you can just plug in that number. And probably should, I don't always do this, but it might be a good idea to put parentheses when you have something like this, a limit like this, just because otherwise it might look like you're just taking the limit of one part and not the other. So another example would be, let's say we're taking the limit as x approaches 2 of -5. So this is a constant function, right? So -5, f of x equals -5 is a constant function. And so in this case, it's kind of a funny example, but you can plug in 2. The thing is just that when you plug a number into a constant function, you just get the same answer always, right? So if the function here is f of x is equal to -5, well then f of 2 is also equal to -5, right? It doesn't matter where you're taking the limit, the function is just always equal to -5. So one last example, let's say that we're taking the limit as x approaches, 5 of x squared minus 3x plus 2 over x minus 1. So we'll do another example with this same function actually in a moment. And basically, if this function, if we were trying to take the limit at 1, then we would run into a problem, right? Because the function's not defined at 1. But because there's no issue with plugging in 5, right? The denominator is only equal to 0 when you plug in 1, not when you plug in 5. So we can just go ahead and plug that number right in. And so we get 25 minus 15 plus 2 divided by 4. And if you simplify that, that comes out to equal 3. So again, I think these examples are easy, but there's almost something a little confusing about them because they're easy. And again, the reason I think that you might have that kind of feeling is because these just aren't really the types of situations where it makes sense to take a limit. Usually when you're taking a limit, it's because the function is undefined or because it's a piecewise function or because there's just something funny going on. But technically, if you're asked to take a limit of a function that is a nice function and it's defined at the number, you can just plug in the number. All right, so next up, we really have kind of the most important rule that we're really going to be focusing on in the remainder of this video and also in tomorrow's video. So what this rule says, and it might not be super obvious how we're going to use this rule at first, but then we'll get into some examples. So I'll even write down, this is the most important rule for evaluating limits. So if you have two functions, f of x and g of x, and let's say that those two functions are completely identical everywhere except for at one specific x value. And we'll see some examples of how those two functions might look in a second. But so if f of x and g of x are identical everywhere except at x is equal to a, then the limit as x approaches a of f of x is going to be the same as the limit as x approaches a of g of x. Because, why is that? It's because, as we've talked about in a few of these videos now, when you're taking a limit, it doesn't really matter what's happening at that specific x value. It matters what's happening close by. So if you have two functions and one of them is defined at a and one of them is not, but otherwise they look the same, the limit is going to be the same when you approach a for both of them. And we actually saw this happen in the last video. We had two functions. We had one that was just sine of x and one was sine of x with a point removed. And we saw that in both situations, the limit as you approach 0 was the same because the only point that was different between those two was the point at 0. So I want to jump into an example and then we'll look at the graph of this, I think, to really understand how this example works. But let's say that we have two functions, f of x is equal to, or I'll start just by writing one function. So actually, same example from the last page, x squared minus 3x plus 2 divided by x minus 1. So you could try to simplify this function, right? This function, the numerator can be factored. So if we were to factor this numerator, we would get x minus 2 times x minus 1, right? That's how that numerator factors, and then we have over x minus 1. And this x minus 1 and this x minus 1 can cancel out. However, I just want to make it really clear that when you cancel a common factor like that, you actually are slightly changing the function. So it would not be correct to say f of x is equal to x minus 2. That would not be true, because f of x has a discontinuity, or sorry, we haven't learned that word yet, but f of x is undefined at x is equal to 1, right? And x minus 2 is totally fine at x is equal to 1. So when you do a simplification, you actually are changing your function. And so let's call this new simplified version g of x. So g of x is equal to x minus 2. So because these two functions, and actually let me pull up the graph right now of these two functions. So right now we have, this is the function, this is the function x squared minus 3x plus 2. And if I scroll to 1, notice that it says it's undefined at 1 as a whole in the graph at 1. And that's because of that denominator, right? That denominator makes this function so it's undefined at 1. So let's compare it now to the simplified version. So the simplified version is g of x is equal to x minus 2. So I'm going to click that on. Notice that they look exactly the same. What's the difference? Well, if we look at x minus 2, now if I scroll along, this one has no issue at 1. I'm not sure if I'll be able to get it to actually hit 1, but there's no hole in this graph, whether I can hit it or not. There you can kind of see. Just trust me, there's no hole in this graph, whereas there was in this graph. So these two functions fit that description that we mentioned earlier, right? Where they look identical everywhere except at x is equal to 1. So let's write that down, and then we'll see how that plays out with limits. So what we just figured out here is that f of x and g of x are identical everywhere except at x is equal to 1. And so that tells us that the limit as x approaches 1 of f of x is going to be the same thing as the limit as x approaches 1 of g of x. So why is that useful? Well, because g of x is defined at x is equal to 1. And so when you have a function that is defined at a number, you can just plug that number in. So we're going to start with f of x. So if we're taking the limit as x approaches 1 of x squared minus 3x plus 2 over x minus 1, if we go in and do that simplification, so we factor the top and we get x minus 1 times x minus 2 divided by x minus 1. We cancel out that x minus 1, which gets rid of the discontinuity, right? It gives us a new function that is now defined at 1. And so now we have the limit as x approaches 1 of x minus 2. And now we can just plug in 1, right? We can use direct substitution. Because the function is defined, we can just plug the number in. So the main kind of objective here is you start with a function that is undefined at 1, right? And we did simplification. And by doing the simplification, we ended up with a new function that is defined at 1. And because that function is defined at 1, we can plug that number, we can plug 1 into that function, and that will give us the answer. So this original function here was f of x, right? This function is f of x. The simplified version is g of x, so that's this function here. And because those functions were identical everywhere except for at 1, we were able to say that their limits were the same. And looking at the graph, we can see that that's true, right? So if we were to take the limit as x approaches 1 of this, the original function f of x, by looking at the graph, we would say the limit was -1, right? Because even though there's a hole at 1, if I can get there, sorry, it's really hard to get it to, there we go. Even though there's a hole at 1, we can see that the graph is heading towards a y value of -1. And so that's the answer we would find. And that's exactly the answer you get that if you plug 1 into this blue simplified version of the function. So this is basically how we're going to be doing limits in the rest of this video, and then also in the next video, is this idea of using algebra to simplify your function in order to be able to plug a number in. So there's going to be a few different methods that we're going to use, and I'm going to write them down, and 2 of them we'll be doing in this video, and then the next 2 will be in the next video. So algebraic simplification methods for limits. So the first one is what we just did, right? So what I'm going to describe that as is factoring and canceling. So factor and cancel. So let's do one more example of that, and then we'll see one other type of method we can use. So example of factor and cancel, or another example of factor and cancel, would be if we were trying to take the limit as x approaches -2 of x cubed minus 4x, all divided by x plus 2. So first thing you always want to check anytime you're taking a limit, especially if it's not a piecewise function, if it's like just a nice function, check whether you can plug in the number. You can't in this case, right? If you try to plug in -2, you get 0 in the denominator, and that's not allowed. And so that's what tells us, okay, we should look for some algebra to do, some ways to simplify this. So how can this be simplified or factored in order to simplify it? Well, the numerator, we can factor out an x, right? So we have the limit as x approaches -2. We factor out that x, and we're left with x squared minus 4. And then in the denominator, we have x plus 2. So from here, x squared minus 4, that can be factored again, right? That is a difference of squares. So we have x times x plus 2 times x minus 2. That's how you factor x squared minus 4 is a difference of squares. It factors as x plus 2 times x minus 2. And then we're dividing by x plus 2. And so we can cancel out this common factor of x plus 2, and that gives us a new function. So we're now taking the limit of this new function, and the new function is x times x minus 2. Or if you wanted to, you could rewrite that as x squared minus 2x. So just to be clear, that is a different function than the one we started with, but we'll look at the graphs in a second and we'll see that it looks really similar. It's just that it doesn't have a hole, it doesn't have an issue anymore at -2, and so now we can actually go ahead and plug in -2. So if we plug in -2, we have -2 squared minus 2 times -2. So that's going to be equal to 4, and then this becomes plus 4. So that's 8. Okay, so that's one method. The next method that we're going to be doing in this video is what we'll call expand and simplify. So an example of expanding and simplifying could look like this. So let's say that we're trying to take the limit as x approaches 0 of 3 plus x squared minus 9 divided by x. So we can't plug in x, right, because the function is undefined as, or sorry, we can't plug in 0 for x because we would get divided by 0, which is not allowed. So in this case, what can we do to simplify this? Well, we can actually multiply out 3 plus x squared and see what that gives us, and we'll see that that will allow us to further simplify this. So if we multiply out 3 plus x squared, so remember that when you're multiplying something like this, maybe I'll do this over here. 3 plus x squared means 3 plus x times 3 plus x, right? So you have to actually multiply it out. You can't just say 9 plus x squared. That would be wrong. So 3 plus x times 3 plus x is going to give us 9 plus 6x plus x squared. And then we still have minus 9 all divided by x. So the numerator, the 9s are going to cancel out, right? We have a 9 here and a 9 here, so those go away, and we're left with the limit as x approaches 0 of 6x plus x squared divided by x. And in the numerator, notice everything has a common factor of x, so we can factor an x out. And that leaves us with 6 plus x. And when you're simplifying things like this, like when you're simplifying a rational expression where you have a numerator and a denominator, it's really common for people to make mistakes. So one mistake that I might see people make is they might just cancel these x's, but that would be wrong because you can't just cancel out one part of the numerator. You can only cancel something when it's a common factor of the numerator and the denominator. And being a common factor of the numerator means it has to be a factor of everything. So I think the easiest way to avoid making that mistake is to make sure whatever it is you're trying to cancel, make sure you can factor it out from the entire numerator. And that way I think you'll avoid these sort of mistaken cancellations that are not really complete. So here, because we could factor x out from both terms in the numerator, we can see, oh, okay, that is a common factor and we can cancel it. And so now we're left with the limit as x approaches 0 of 6 plus x. And now we can just plug in 0, right? Because now there's no issue with plugging in 0. And so we get 6 plus 0, which is equal to 6. So let's look at the graphs for both of these two. I forgot to show you for the last one. So the first one we had x cubed minus 4x over x plus 2. So that's this. So this is the original function. And if we go to -2, an x value of -2, we see that there is a hole in the graph at -2. Hopefully you saw it there, right? So there's a hole in the graph at -2. So this function is not defined at -2. That's why we couldn't just plug -2 in. However, if we look at the simplified version, so if you remember, after we factored and canceled, we were left with x squared minus 2x. And so that's this graph in blue. And notice they look completely identical. The only difference is that there's no hole in this graph at -2. If you go to an x value of -2, just trust me that there's no hole there. And we can see that the y value is 8. And so we are allowed to just plug that in. Similarly, the one we just did looked like this. So this is 3 plus x squared minus 9 over x. And this one has a hole at 0. It's undefined at 0. There we go. And we simplified it, and our simplified version was 6 plus x. And that looks exactly the same, except for that this one does not have a hole at x is equal to 0. And so we could just plug in 0 and we got 6 as our output. So again, it's just this idea of simplifying in order to give you something that you can actually just plug a number into. So there's two more methods I just want to mention here, and these are the ones that we'll get to in the next video. So one of them is what's called multiplying by the conjugate. And so this is going to be basically to get rid of square roots, and we'll see what that looks like in the next video. And then the last kind of algebra that we'll be using is we're going to be making a common denominator. And so that's going to happen when you have either multiple fractions or you have a fraction within a fraction, oftentimes making a common denominator is what you'll need in order to be able to do the simplification so that you can plug the number in. So these two are both in the next video. All right, so that is it. It's really important, I think, especially today, that you do the worksheet that goes with this, because there's just a lot of different types of factoring that can show up, and you know, that's not something that we spend a whole lot of time on in Pre-Calc 2, so it's something that you probably need a little refresher on. So I'd really recommend that you attempt the worksheet for today, and yeah, I'll see you in the next video.